Thank you very much. I'm really happy and glad to be here. First, one word regarding the fact that I've not been present so much in Italian conferences, and being Italian is actually really an honor for me to be here. Thank you. So let's go ahead directly with glitching devices for code execution. And the goals of this presentation are discuss how FI attacks, fault injection attacks, we're going to use FI along the presentation for indicating fault injection. They can be used to gain arbitrary code execution on devices. Actually, on any target which is glitchable, but we are focusing here on devices. And this can be done regardless of the CPU architectures, and even in absence of software vulnerabilities. We are going also to show how software-based countermeasures, because you have fault injection attacks. The industry and academia have developed countermeasures against these attacks. There are hardware-based and software-based ones. We are going to show how, with new techniques, we can actually bypass the software-based countermeasures. We are going also to discuss how such techniques may allow to loosen timing requirements. So one of the usual requirements is that you hear is that fault injection attacks needs to be very precise. You need to target that instruction. You need to be a very good time, to have a very good timing and a good synchronization with target. We're going to discuss how this can be loosened to the point that your trigger may actually not be very precise, sometimes not even exist. That's why, just a bit provocative, I'm talking about quasi-triggerless attacks. So basically, I hope that this kind of reflection can contribute to the field and to the reflection of everybody doing fault injection attacks or any hardware security. So the agenda here is that we're talking about the foundation, some introduction which is functional to what we need to discuss. Then we're trying to give a bit of systematization to what we see and what we see often discussed, trying to put some terminology and concept in the right place. We are going to discuss which are these countermeasures and also how it's possible to achieve program counter control and also bypassing the countermeasure, while also arriving to the point that you may not need even a precise trigger anymore. So let's dive directly into the foundation. Well, fault injection is not something that we invented. Actually, nature invented that. So the first reports that we actually see is in 1979, where fault injection, like cosmic rays, have had a proven effect, which were otherwise unexplainable on memories. So this has been actually proven. These are peer-reviewed scientific research, by the way, so it's not something that is really happened and proven. Also, we see radiation being able to do that. It's not something that we have created. What we have created, actually, are the attacks that may leverage such effects. So the first known attacks, at least known to me, in terms of fault injection, was defined a way of breaking an RSA signature. So if you actually perform an RSA signature by using CRT, which is actually the fastest way of performing a signature, and you inject one single fault, you just need a good signature and a wrong signature. You get together and you get the private key. That's what you need, a single good fault. This actually has been discussed and proven and demonstrated in 1996 in terms of academia. So these attacks actually has been performed. This is also called umbrella core attack. So this shows that the academia already in 1996 had already figured out way of using faults. Not only even attackers have used, figured out ways of using these fault injection attacks. You may remember at the end of the 90s, some of you actually are aware, let's say, using fault injection for using unloopers. So you had a smart card, which was used for payment of PayTV. Then after some point in time, or after some attacks, these actually went to infinite loop, and using fault injection, we get them out of the infinite loop. That's why they are called unloopers. It was used for clock glitching, and it was for reviving how the smart card jump out of an infinite loop. So the traditional attacks are always aimed to either break some crypto, so changing some data, or bypassing some checks. This has been the usual way of using fault injection attacks. I think you are more or less familiar. I see people nodding and really happy about it. So if you think about, let's say, the usual way of bypassing checks for bypassing a secure boot, so this is just a sample code of secure boot. What you see there is that you have the secure boot actually loads the boot stage to be verified into memory, and it loads to an address It's just the image address over there. Then basically, it actually loads the signature in order into memory. And then this signature is verified. I will not go into the details, but this involves more or less computing the hash of the stage, decrypting the signature, taking the hash from the signature and comparing them. That's more or less what it entails to verify the signature in general. If this is wrong, you actually reset the chip. If this is correct, you progress to the stage which has been verified. Of course, I mean, you need to have the private key in order to produce that signature. So in general, if you have a secure boot process, you would not be able to bypass it normally unless there are logical vulnerabilities. So one of the usual attacks of fault injection, which are applied to, for example, secure boot, but in any case to checks, are you load a malicious boot stage. Of course, the signature, which will be still loaded, will not match anymore because you don't have the private key. So this verification actually would fail. But if you actually, usually the approach is to glitch this verified signature in order to execute the image, even if the boot stage is wrong. So this is the typical textbook attack for secure boot. Okay, so there is really nothing special over here. And this has been proven several times in the last 10 or 15 years. So this is not even news anymore. This is where we start from, though. Why does it work? Well, the typical description why it does work is that you are skipping instructions. It's in instruction skipping between quotes. Because the glitch is assumed to skip instruction, regardless if this is true, this is the effect that you see. So you see this effect. So it's actually legitimate to call it instruction skipping. Then we can always discuss if this is really happening that way or not, but that's another point. What you see is that an instruction is being skipped. A conditional instruction skipped is then not executed. So this means that that if will not be checked properly and the execution will continue on. And this will lead you, in many cases, to execute the wrong image you have just loaded. So this is the description that you will find in academia industry. So I would say, an estimate, 80–90% of the papers that you see outside, or talks, or blog posts that discuss about glitching, basically they refer to you skip some instruction and you go ahead. Now, this means that the attack modeling has been dominated for fault injection. One moment, I need to fix. I hope this is better. So this dominated attack modeling for fault injection for the last 30 years. So this means that with this in mind, we have also designed countermeasures in general along this idea. This was with the first fault model. So when you actually need to execute an attack, what do you need? You need to skip that instruction. So this requires accurate timing, really that one, or around that. This means that you need to synchronize with the target, because you need to make sure that you're hitting exactly that one. Actually, this attack is usually executed blindly. So this means that you don't assume that you have some type of fault or another. You just say, hey, let me see if this actually bypasses. You just load the bootloader, it just glitches, just send glitches around, just let it go for hours, days, weeks until it succeeds, and then it succeeds, usually. I mean, the way what we call this called glitch and pray. And it works, it's fine. There's nothing diminutive to that. We're just saying that there is no attack, not so much of an attack design and strategy. So basically, this is an example of an attack that we did on ESP32, but we have been doing this on many devices. It's just that this is public research, we can actually show. So you can see that in this, in the upper part, the bootloader is copied to SRAM. What you are seeing is the chip selected of SPI flash. When you read from flash, there is activity from flash. So when you're copying from flash, that pin is active. It goes up and down. So this means that the flash is being used. So by tracking that pin, we know when the flash is being used, and we know that when bootloader is actually copied into SRAM. And this is why we see that kind of those kind of patterns. The flash is being read, is active. After the bootloader is copied to SRAM, at the end, there is very likely the verification. you cannot verify a bootloader until it's fully in memory. So what you see here is also something triggering. You trigger lower, trigger high. So we wait for a bit in order to wait for a gap in the middle. And then at that point in time, we just trigger it on the first rising edge. And this is how we trigger, so we are synchronized with reading. So basically, we use flash communication for synchronization. We use this signal that tells us, OK, this is being loaded. Now, in order to bypass it, we need to glitch that instruction. So at the end, you know that bootloader is being loaded into SRAM. You want to glitch that if. So it's very likely at the end of that process. So when the loading is finished, we just start glitching around there, glitch and pray. We don't know what's happening. Go. See you in 3 days. If it succeeded, it succeeded. Secure boot bypass, done. Mission accomplished. Well, actually, this was pretty easy to do, but in general, the approach is that you glitch somewhere after the bootloader is copied. It's more or less around there. So there is no control whatsoever. Is it just randomness and luck? Is this all everything that we can do? Well, if you just stop at doing this and trying it, it's pretty much that. If you start thinking about how things work, and that's what we are going to progress, and you actually try to do some systematization of the concept, well, I think we can actually do some, we can move forward. So when you have a fault, why does this fault happen? It happens because of physics. You're putting the device in an environment that it starts misbehaving while still functioning. So it's not completely stopped, but it's not completely functioning as intended. So this means that there is a gray area where there are effects that allows it to misbehave while still keeping on working. Now, these effects happen at the physical level. It's physics. It might be, let's say, we're not going into the details of VCC clock and laser, but maybe, for example, that the values at gate output are not sampled correctly because they are not ready for clock glitching, or because there is not enough energy for representing them, voltage glitching. So this is actually happening somewhere in the chip at the physics level. Of course, on top, there is just the circuit. There is not only the gate, there is a net. You know, the net list that you might have heard, all these things, it's a net. So meaning that the misbehavior of one single gate was going to affect the logic on the rest. Then, of course, I mean, if you go up, there is the microarchitectural level. If you go to CPU, I mean, x86 has a microarchitecture instruction. We have microarchitectural attack, which are slightly below the instruction level. All this here happens more or less in hardware. If you think about the boundary between hardware and software, the software starts existing in a system on chip where the microarchitecture is not configurable. It starts existing at the instruction level. For chip where you can configure, let's say, the behavior instruction with microarchitectural instruction, then the boundary between software and hardware is a bit lower. Then, after instruction, you have the program, the control flow. That's what basically you have. We like to add an additional subsystem in the middle, which actually represents whatever is not a CPU, but is a valid subsystem. So for example, at this level, you can do glitching of things which are not a CPU. You can actually open a JTAG with fault injection, which is closed. And this has nothing to do with CPU. There is no software being glitched. You can actually glitch an OTP behavior, one-time programmable, the configuration in hardware. And this has nothing to do with the CPU. So you can affect the hardware logic, basically how it works. So what we have to understand is that once we have something which is misbehaving at the physical level, this means that that kind of misbehaving at the physical level may cause the device to misbehave in multiple manners. And it's not easily predictable. So the changing of one bit, let's say, in the representation of a single gate, it's very difficult to understand how it's going to propagate in the system. You cannot really easily predict that. That single bit can actually cause multiple effects. Not only, once you actually glitch, you may have a situation where basically you are zeroing an entire register, or you might flipping one single bit, or you might silencing one single subcomponent. You cannot predict what is going to happen really at in the device. So that single glitch, if you repeat several times, may yield different kind of effects in the system. So basically, what we call a fault model. A fault model is something that describes what you're interested in. We call instruction skipping all the faults that allow you to give an effect which is similar to an instruction skipping. We don't know if it's going to flip a bit to zero something, to silence a subsystem or a component. We have no idea. The effect at the upper level is that you skip an instruction. So we don't know if you really skip an instruction or not when you're doing a glitch. But we need to understand when we are glitching, many things happen or can happen. So for example, if you're thinking about using instruction skipping for an attack, this is what we've been using before for the secure boot. We use instruction skipping, we skip that if or at the assembly level, and then we use it for an attack. You can actually start thinking, okay, I can flip this bit, I can zero this other one, and then other attacks are possible. But what we think we need to understand is that in order for this to be effective, there must be a hardware vulnerability. And this is actually modeling an FI attack allows us to understand how it works. So there is a hardware vulnerability, there is a technique, inject, that allows you to trigger this vulnerability with some parameters. For example, you need to do voltage within these parameters. That is going to generate some fault, and that fault may be different, depending on what kind of techniques you are using. And then you have an exploit. For example, in our case, the instruction skipping can be used for bypassing security checks in general. Of course, I mean, you can qualify, you can describe more about these single fields or the single points in the modeling. And if you want to, you can actually go deeper into that. What are the key points? Is that when you have a vulnerability, it means that the target is sensitive to a technique. The vulnerability is always in hardware. Whatever you do in software can only help or mitigate the exploitability of that. You don't solve things in software, in fault injection. You mitigate things in software, if possible at all. Not only, the same vulnerability, when triggered, will give different kind of faults. And once you have a fault, it can generate things which are interesting for multiple fault models. We are seeing this in a moment. And once you have a different fault model, like instead of skipping an instruction, we can zero this register. If you can zero this register, I can zero variables. Then I can think of another attacker, or another kind of attack. Every time you think of a fault model, you can build a different attack. Now, this is why I'm talking about this. Because all the countermeasures in software are based in implementation of software. We are going to see a few of them. Example, how do you implement the countermeasure for the secure boot attack in the industry we've seen? For example, you do the verify signature multiple times. This is a typical approach. It's one of the many, actually. And why? The assumption is that a glitch is required in every check. So if you can target the first if, then you need a second glitch for targeting a second if. And then you need a third glitch for targeting the third glitch, the third signature verification. So this means that the complexity of the attack is much higher, under the assumption that you really need 3 glitches, because you are targeting that if you're targeting conditional. Of course, I mean, you still need to be precise. So another countermeasure is inserting random delays so that your target moves. It's random where it is in time. So this means that hitting the first if will be difficult, the second if will be even more difficult, and the third if will be close to impossible. But I can tell you by experience that these techniques actually are effective against this fault model. So if you start thinking of skipping checks or skipping instruction, this can easily become a nightmare for an actual attack. So they are effective. But they are effective because, again, the location in time is not fixed anymore, under the assumption that you must hit that specific point in time. And this is actually widely used in industry and academia. Nowadays, when you hear about, yes, we have implemented fault injection countermeasures, there are only 2 ways. Either you redo your hardware, or if you're lucky to have an FPGA, then probably you can reconfigure your hardware, but that is not the case usually. Or if you're doing in software, this is what you're doing. Or many of the things that you're doing are probably similar like this. These are not the only ones, these are just 2 prominent examples. So this is commonly advised and implemented in FI-resistant targets. Of course, I mean, this makes the attack really difficult, and there are studies of quantification, which actually depends by target. Now, my goal here is to make you reflect that there is one big untold assumption. First, that in order to have those countermeasures in software, this means that the software must be executed. And that's the first one. There is another fact that the attack that they have in mind with this countermeasure is expected to focus on those checks. And also it needs to be very precise in time. So they're making us hit more times and with more difficult targeting because of timing. So this assumes that the default model using for your attack is instruction skipping. So this means that whatever you had in mind, what you have created, is based on skipping instruction. But what if we switch to a completely different fault model? Instruction corruption. I mean, a glitch in principle can change stuff, right? It can affect the physics. So it means it can affect instructions when they are loaded. So in principle, you can change those instructions. So this means that glitches may corrupt instruction. For example, number 32. Again, this is not an hypothesis. I'm telling you things which have already been proven by research. So this is not something that I'm arguing is possible. We have demonstrated, not only us, but mostly us, I mean, we have demonstrated this is possible in peer-reviewed papers. Just to tell you what, this is reality. It's not an assumption and hypothesis. Glitches in many cases corrupt instruction, can. Think about that single bit corruption. You have an add, this is an ARM32 assembly, something understandable. The register X3, by flipping a single bit, is changed to X2. So this means that now you are loading into X0 the sum of X1 and X2, instead of the sum of X1 and X3. And this is just by flipping one bit. How does it work? When you fetch an instruction, you fetch it from memory. It goes over bus. If you glitch the transfer and change that bit, this is what you get. Of course, even multi-bit corruption may happen, and this is another example. You don't control what really happened. You're only interested if that actually happens, because then you can use it. Most chips are actually affected by this fault model, so which bit can be controlled, how, at which timing, really depends on the characterization you need to do. You need to study the target. But in general, this actually modifies software. And if you can modify the software which is being executed, the software security model breaks. I mean, this seems abstract. Let's have a look at the actual practice of this. Now, think about data transfer. We actually transfer data in every device, every moment. One of the most successful functions in history of software is memcpy. We copy data between buffers. All devices transfer data from memory to memory, from buffer to buffer in general. Also, they use external interfaces. You have basically the I/O ring in the kernel, which can be used for transferring data somewhere else. You have the packets of network, which go through the stack. Of course, there is not much copying over there, but sooner or later, there will be a copying somewhere. So there are situations where the data which is under transfer is under your control. You are creating the data which is being submitted to the device. When you're doing a syscall, you are the one controlling the data and submitting that to the syscall, for example. So memcpy, basically it's everywhere. I mean, if you look at memcpy, when we do software security review, we look at destination, source, and the size. Yeah, you need to make sure that the destination is within safe boundaries, that the source is within safe boundaries, that the amount of the size being transferred is not too large for the destination buffer. But what you actually transfer is not security critical. It's not considered as such. You can transfer banana, apples, lime, whatever. It would be the same from a security point of view, right? Now, if you start using this as a fault injection target, well, there is something extremely relevant to the data which is being transferred. Now, think that you are basically providing data over transfer over the interface over USB. There is an input buffer. Then this command is being handled somewhere. Command handler processes this data and actually responds to you. At some point in between, there is an memcpy, you see? So what you're seeing that the attacker data is being transferred. You see those two instructions, LDM R1 and STM R0. So this means that you take the data which is pointed by R1 and you store it into R3, R4, R5, R6. This is how you read that first instruction. R1 is a pointer, and you get data into those registers, right? And then you store the content of those registers to R0, to the destination. So R1 is your source, and R0 is your destination, right? So the first instruction copies 4 times 4 byte, so 16 byte, and the second instruction stores at destination 16 bytes. Now, look at that line. Now, if you glitch during that line and you change one of the bits of the register, then one of the registers may become the program counter. This means that the data that is being transferred goes directly into your program counter. So what happens when you transfer something to a program counter? Basically, your PC is set to attacker data, and the control flow is directly ejected. The continuation of the execution will go from the address that you have set. This is pretty interesting. You send data, whatever, you glitch, it ends up in program counter, and then you magically start executing from somewhere else. Again, this is what happens. It's not what I argue it may happen. This has been proven to happen. So this was an easy explanation for ARM32. You basically corrupt an instruction, you modify this load instruction, and then you modify the PC, just because you flip one bit or a few bits in the destination. We're using this several times. We demonstrate this publicly. I mean, I will not go through this, but there will be links around to investigate. Does it work on other architectures? Because in the end, being able to change something to PC is specifically to ARMv7, ARM32, only that. There are very few architectures where PC is addressable. This is not a problem. We have multiple variants that allow you to give you code execution, and which are sufficiently generic to work across multiple architecture. For example, you could corrupt the stack pointers. It's still a register. Instead of loading to PC, you could still load to stack. And then the entire world of ROP and, let's say, shadow stack and other things, pivoting, for stack pivoting, can actually be used. So there are examples for this, but let me show one which is important. For in ARMv8, you have an instruction which is called ret. You return from a subroutine. Usually, the return address is in one register, x30. So when you enter, you don't store the value on the stack immediately. You store in x30, okay? The instruction is this encoding. You see this? In principle, the instruction ret can encode more registers, not only x30. Many people see ret and think it's x30, but the instruction, the assembly, leaves room for encoding. So if you flip one bit there, you will return to the register, to the address stored in a different register and not x30. Real world example, this is Google Bionic memcpy. We are copying that code, look at that. Then the source is in x6, and the destination is in x7, basically. So, sorry, source data reside in x6 and x7. So x6 and x7 contains your data, okay? So this is something that you control. x1 is the source. Now, if at the end of the function you glitch that ret to ret x6 or ret x7, you will jump to the data that you control. So this gives you the ability to control program counter on any architecture, because this is what happens on basically any architecture in general. So basically, how do you do this? First, you identify data transfers that you control. I mean, USB interfacing, serial, whatever. memcpy being kernel, okay? Put your shellcode somewhere reachable. In the data that you transfer, put pointers and start glitching. Glitching during any memcpy, you get PC control, and then it's like having a Stack Overflow, but without any software vulnerability. You get control of PC, but you have not done any buffer overflow. So stack canaries will not be relevant to anybody. What will be relevant is from that point where you jump to. ASLR may be effective. NX, non-executable memory pages, will be effective. So basically, if you actually go like this and you actually set your payload, your sled of pointers, and you glitch during your pointer sled, this means that your execution will be very similar like this. When you load your pointers, you glitch, they go into the program counter, your program counter starts executing the payload, which has not been verified. Nothing has been verified yet. So you start executing your payload before any check actually happens. Why? Because the checks do not exist anymore. Because that software is not executed. It's there, but the program counter starts executing from somewhere else. The key point is that the software-based countermeasure becomes completely ineffective. All of them. I'm talking about all the devices which have this kind of countermeasures. If you glitch during the data transfer and not glitching the instruction, then an entire world opens up because the countermeasures are not there anymore. So this means that you don't target checks anymore. You don't care. All those countermeasures which are in there, basically, they're not even existing anymore. This is very hard to protect against, and today is applicable to fault injection resistant target. So when you see targets which are deemed to be fault injection resistant, instead of attacking the checks like everybody does from a textbook, try to attack a transfer where you control the data. If you look at the assembly and the reversing, that there is an MCPY or any data transfer instruction, any load, glitch there. You will likely be successful. And this is example of what we did. You see that those lines over there, that small block of around 204 microseconds, is not at the end. The area that we are glitching is within the copy. Now we are glitching while the data is copied. And what is copied? Pointers. We had the payload somewhere else. It's just copying pointers. Nobody checks that you're copying pointers because nobody knows what you are transferring. The transfer is agnostic to the data itself. So you can put whatever you want if you control there. So we control a small attack window while the bootloader is being copied. Well, to give you the proof of success, this is what we achieved. Basically, we got control of the program counter every 30 seconds with this technique, regardless of all the checks that may have been afterwards. So let me add something really relevant, because people think that you need very precise synchronization, timing. Now, with this technique, basically, this actually goes away. And there is a few reasons that allow me to basically conclude my talk. The MemCPY actually loads data into register. There is a load instruction. That load is done in loops. How many loops? Depends on the size which are being transferred. When you glitch, you modify the instruction so that loads this into another register. And the control flow is ejected only at function exit, not during the transfer. So this means that these loops will happen so many times before the function exit that you will have several and many opportunities for glitching. It's not anymore one single thing, one single point to attack. So basically, you can glitch anytime, anywhere. Or you have a very big window where you can actually glitch. And not only, what you see is the example that even if you think there is only one single MemCPY, actually the device is reality to transfer code and data many times. So what you're seeing here is kernel transferring data after a syscall. So we did a syscall, we put data into register, and we just start glitching until the end. Now, we have successes of getting PC control into kernel at that time, at that time, at that time, that time, and that time. So this tells you already that the data that you have used for submitting the syscall have at least been transferred several times. So if you start glitching during this time, you may very well encounter any data transfer. So instead of transferring payloads, of transferring shellcode, transfer pointers and start glitching and see what happens. If you get your pointer into PC, well, you're definitely onto something which is definitely different from the usual attacks. So basically, you have very large time windows for glitching. Any data transfer can be a target. You need very loose synchronization. You don't need to be precise anymore, basically. And sometimes the precise triggering is not required anymore because you have such a big window. Why do you even trigger precisely? Why do you spend so much time in hitting there? You don't need there. There is like this. So this actually brings you to a situation where your trigger becomes much more relevant. Your precision is much less relevant. Sorry. So let me add the following consideration. All the countermeasures in software, or most of them, are based on instruction skipping. If you use another fault model, they may, like in this case, completely disappear. Instruction corruption actually gives you code execution. It's very natural because you get PC control with those kind of attacks. What you only require are control of the data being transferred. Any data transfer can be a target, and your setup may become much easier in terms of synchronization. You don't need very split microsecond or nanosecond precise. And more and strong targets out there are still vulnerable to this kind of attacks. So when you see a device or, let's say, a target which claims to be fault injection resistant, again, my advice is not try to execute and bypass checks. Transfer data, pointers, and glitch. Still glitch and pray, but it will be glitch and see. Because if your PC goes to one of your data, then you get PC control. And I hope that this has been interesting for you because should shed some light on how to implement different fault injection attacks. Thank you.